So we will essentially talk about Lie groups today. Okay, that's our topic. And oops. And if you look at Lie groups in some books, especially in mathematics books, then it may end up looking very, very different from what you would see in a physics textbook. And one of the major reasons is a Lie group essentially is a differentiable manifold which is also a group. Um, well, I'm pretty sure most of you know what differentiable manifold means, but roughly speaking, it's a set on which you can do calculus. The mechanism for doing calculus has been made available somehow on this set. Uh, the reason why I say it has been made available somehow is that differentiation and integration, the basic rules, things that you do in calculus, can strictly speaking be done only on very special sets, basically only on Rn. So differential manifolds are sets which can be made to locally look like Rn. If not, if they may be very different globally, but at least chunks of it can look flat and like Rn. Of course, the different chunks may sit together and add together in a very complicated fashion. And even if it's not in such a complicated fashion, it might still lead to things like curvature, etc., which are of great importance. But the important thing in a differentiable manifold is locally it looks like a flat Rn. And basically, what you do is you essentially translate things from the manifold to Rn when you do calculus. But that structure has to be made available. An arbitrary set is something you can't do calculus on. To do calculus, you need this additional structure which the differential manifold provides you. Now, depending on what aspect of the group you are focusing on, some people would focus on the differentiable manifold aspect where the group is just an additional structure. And very often, some people would focus on the group structure where differential manifold is something which is an auxiliary part, which comes in to help in the group structure in some way. So, depending on your focus, different texts, different people treat Lie groups in very, very different ways. So different that you may not even be able to recognize that they're talking about the same thing. But it's basically the same thing seen from different aspects. And for us, phases, I'm not going to say that Lie groups per se is never important and Lie algebra is all that is important. Simply because, say, for example, the kind of work I used to do at the in my PhD work, there the Lie algebra was really incidental. The Lie group was more central. Although for calculation purposes, we needed the Lie algebra as well. So it's wrong to say that Lie groups are never needed in physics. It's only the Lie algebra which people need. However, it's true that a major part of the applications of the Lie group theory to physics is essentially that of Lie algebra. So I will, because we're running short of time, what we're going to do is we're not going to delve into the full Lie group theory. I will try to get as soon as possible into Lie algebras, and I will cut some corners. Some of the proofs will not be as rigorous as they should be. Okay. However, basically, so the very first thing we would say is something like this. Lie group, of course, being a group has elements, and basically, when you say it's a differential manifold, you also mean that points on the manifold can be labeled by coordinates. So every element essentially is labeled by a bunch of coordinates. So this x bar are basically local coordinates, which if you know the differential manifold language, all you're doing is you're assigning a chart. From that chart, you're reading off local coordinate functions and so on. But all we really want to talk about here right now, all we need is that there's a bunch of parameters, real parameters, let's say R in number, and this bunch of real parameters specify which Lie group element you're talking about. And there is a continuity in this sense that if you change the x1, x2, xr any one of them slightly or all of them slightly, the Lie group element is going to change slightly. Now, exactly what slightly means, exactly what the topology of the differential manifold is, and so on, we are not going to go into that right now. That's not important because in most cases, we are going to deal with matrix groups where how does a matrix change slightly? Or what does it mean when you say a matrix is changing slightly? It's sort of obvious. The components will change slightly. Okay. So, because most of our applications will deal with a situation where notion of proximity or in more mathematical language, notion of topology is sort of a given notion, we will not bother so much about being more rigorous about exactly what continuously maps into the group means. For most of our applications, that will be sort of obvious from the context. Okay? What is important is, of course, that when you combine two such group elements, you are going to get a group element which will be parameterized by some parameters. And in a Lie group, this is what really part of what makes it a Lie group. Uh, the Z bar, of course, Z bar is really not one Z, it's basically are different Z numbers. So let's write the function separately. So Z alpha, where alpha runs from 1 over 1 to R, Z alpha is some function phi alpha of the two R variables, the two R components, R of X, R of Y. Okay. And this a part of the definition of a Lie group is that this function should be an analytic function. Well, essentially, it's arbitrarily differentiable function. That's all we need for the time being. So that's one half of what you require in a Lie group. If you forget about the differential manifold structure and all the background, what you would say is, okay, I have a bunch of parameters x1 to xr, real parameters. The parameters help us to label a group element. And of course, if you compose group elements together, you're going to get a new group element. So the parameters of the new group element will depend on the parameters of the original group elements that you're composing. And this dependence should be expressible by analytic functions. Not one analytic function, but really R analytic functions of two R variables each. Okay? So that basically is our version of Lie group. We are going to talk about the parameterized version rather than the abstract differential geometric version. Now, one thing that we always do, this is a choice, but you can always choose this. You can choose your parameterization in such a way that G0 bar is the identity of the group. That is, I'm going to choose my parameterization in such a way that the origin of Rn, of R, capital R actually, this is the space where my parameters live, the origin of that space is going to stand for the identity in the group. That can always be done by trivially changing the parameterization. And since this is going to definitely work, this immediately puts some restrictions on these functions. These functions cannot be any arbitrary analytic functions. You must have this property that if you took the alpha function phi alpha, give x as a first coordinate, but a bunch of zeros as the next arguments, you will definitely end up with x alpha. Okay? And not only that, if the first R arguments were 0 and the next R were x, then also you're going to end up with x alpha, where alpha, of course, is the R plus alpha argument here.
So you mean Z alpha?
Well, no longer Z alpha, right? Because gx,
Yes,
g0 has
yes.
to be gx, right?
Yes, yes,
That's
yes.
because we're dealing with identity. So whatever x you put in, that comes out. I meant Z alpha originally when I talked about this, but that was when I put in arbitrary x and y. Here, if I am putting x and 0, I am bound to get back x. That's a basic group theoretical aspect creeping in. That identity always gives you back whatever you had. Okay.
Yes, sir.
Sir, what did you mean by R plus alpha term?
So I'm saying R plus alpha is argument of the function phi alpha. If you focus on the function rather than the arguments, there are R zeros here, right? When you say zero with a bar below, I really mean it's not a single zero. There are R zeros here. Then you have x1, x2, x3, xr,
Oh, okay.
right? So this is the R plus alpha is argument of phi alpha. Of course, we would usually say x alpha without clarifying that because that should be obvious. Okay, it's a alpha is component of x, but the R plus alpha is the argument of the function. So what I'm trying to say is the function cannot be arbitrary. There would be some very important restrictions which come in because of the group structure, and that ultimately is what decides what all the algebra that we are going to do essentially follows from this kind of restrictions. Okay. In fact, one immediate restriction which comes in immediately from here, which is this: if you take the functions and carried out the derivative, sorry, I should be consistent, so I should put the bars below. The bar here essentially says that these are vectors. I just didn't want to put an arrow so that that might confuse with ordinary vectors. This is an R vector in the small r dimensional space, parameter space. So what will this be?
Delta alpha beta.
That will be delta alpha beta. That's sort of obvious. Well, usually when you're talking of derivatives, perhaps a better idea to sort of not, I could, instead of calling, I'm going to call x, when I'm writing it this way, I mean the first arguments, r arguments are x1, x2, xr. The next r arguments are y1, y2, yr. So I'm just going to focus on that. But if you do this, this follows from this result that if you were to put in y beta here, y here, you're going to get y alpha. And then just do the derivative, this is what you're going to get. So these are properties of the function which follow automatically from the group structure. Another property, a more involved property, but an important property nonetheless, follows from this. If you calculated this thing, that will be a group element, but we know a basic property of the group is that this must follow, right? Okay? That's just associativity of the group. But what does it tell you about the function phi that we talked about? Notice that if you look at this element, of course, is some w, right? G of w bar, right? Both this and this are the same G of w bar, where w bar is some bunch of parameters. And if you look at that, say that this has to be the same both ways around, you will end up with this result. So the functions phi alpha should obey properties like these. Okay? And in fact, this turns out to be a very important property, and in dealing with the Lie algebraic structure of the theory, we are not going to perhaps use these properties all that extensively because as I said, I'm going to take a shortcut and get into Lie algebra as soon as possible. But in a full-fledged theory of Lie groups, these properties of the parameterization function play a very important role.
Sir, do
Yeah.
we have any restriction on phi coming from the invertibility?
Yeah, that's the next thing that I'm going to talk about. This is g of x inverse. Sorry, that's wrong. There is the x's don't necessarily form a group, or even if they do, that group structure has nothing to do with our group structure. This is what will happen, right? That is, every g of x bar is a group element. It has an inverse, which I can write as gy bar. And y bar will be some function. Sorry, not I. The y alpha, the alpha s parameter will be some function I alpha of this x bar. And of course, this will have a property that if you take the rx's and then you take the r, so this bar under the I essentially means I'm going to take I1, I2, IR and put all of them together. And also I'll take the alpha component of this. So what must this be?
E.
No, this should be close, but this is not E. You should not confuse the parameters with the group elements. This is the
Zero.
parameter. This will be zero, right? The parameterization. This is the alpha component of the of the group element that you get when you compose g of x bar with g of ix bar.
Yes, yes.
And this is of course y. So basically what you're saying is you're composing gx with with this inverse, and you're going to get the identity. This is identity, of course, which is g of 0 bar. So you are looking at the alpha component of that parameter, and that comes out with 0. Of course, one of the important things in the facility that we have in dealing with Lie groups and stuff like that is that the parameters can be used interchangeably often. For if you're talking about the group elements themselves, you talk about the parameters. That, by the way, is what we do in differential geometry all the time. Instead of talking of actual points on the manifold, you talk of coordinates. Instead of talking of points on the Earth's surface, you talk of latitudes and longitudes, which are just pair of numbers, right? So we do that all the time. However, it's important to realize that one bunch is a parameter and the other is a group element it refers to. So here these numbers, these are just numbers, they will come out to be zero. The important restriction, this is not a restriction, this is just part of a definition. The important restriction, which is the second half of the defining property for the Lie group, at least in the parameter language, is this also should be analytic function of components of x bar, that is of x1, x2, xr. So basically, this completes really what we mean by a Lie group. A Lie group would have group elements which are parameterized by a bunch of parameters, with the restriction that when you compose the group elements, the parameters, of course, will combine together to give you a new bunch of parameters for the composed element, and the function which describes this must be an analytic function. An analytic function. This analytic function must have some restrictions. These are restrictions on that analytic function. But also, it should be possible for you to find, this analytic function must be such that it must be possible to find inverse functions which essentially give you this property. And this inverse function must be an analytic function of components of x bar. So that's the restriction, complete restriction, which defines the Lie group for us. Okay? That's not the cleanest way of defining Lie groups. Perhaps the cleanest way of defining Lie groups would be via a differential manifold definition. Okay, it's sort of like in a way, it's the same kind of thing that we are having here, as when you define a vector. How do you define a vector in physics? How would you do that? When I say physics, I mean advanced physics, not class 12, but now that you are in the fifth year. How would you define a vector? Say a differential geometric definition of vector, quote unquote. That was a question meant for you, right? So I want an answer. Say anybody who has done a GR course.
derivation on the space of functions on the manifold.
That's when you learn way too much.
or maybe
But
the
when you went
something which
elementary GR course, what do you learn?
set of numbers which transform
Yeah. So
in
you
the
have
same
that's
way
exactly what
as.
I meant. You're right. You have a set of numbers which transform in a particular way when you transform your coordinates, right? Now that is a definition which is perfectly handy. It's useful. You can prove a lot of results with it. You can do a lot of calculations with it. In fact, elementary general relativity courses are given almost entirely with this definition of the vector in mind. But you would realize that this definition is rather ugly, right? If you think of it, uh, why would you want to define a vector as a bunch of numbers is still fine? Then why is transformation rule? And then you say a tensor is something which has a different transformation rule and so on. Well, the real point is if you look at the differential geometric definition, where you can have even within that framework you have different. When I say differential geometric, I mean the real differential geometric definition. Even there within that framework, there are different ways of expressing what a vector is. In fact, what you said a while ago is not really the vector; it's a vector field. Uh, but a vector, say, you can define a tangent vector to a curve in a coordinate independent manner, and so on. That has an aesthetic simplicity. Although it's much less familiar to us and it's often more difficult for us to handle because we are more used to dealing with numbers. Geometry is something which we don't understand that well. Algebra is something we understand better. Uh, However, having said that, once you have that geometric understanding of why a vector is defined that way, then the coordinate definition of the vector automatically becomes a consequence. Okay? If you know how you define tangent vectors and then vectors in as elements of a tangent manifold, tangent plane, then when you change your chart, or rather when your chart has overlaps and you have possibility of using different coordinates at the same point on the manifold, which is what you call a coordinate transformation really, um, why is it that vector components transform in that particular manner? That becomes an automatic thing. It's not a definition any longer. It's an automatic consequence of a more, well, more pleasant definition that way. So the reason why I bring this up is we are defining the Lie group via this composition functions and demanding that the composition functions and inverse functions have certain properties. That's basically because we are looking at the Lie group from this angle of composition functions, which is actually convenient and easy to use. It's fast. This gets us to our final goal faster. At the same time, it has this ugliness to it that there are too many pieces. You are talking of phi's and then phi's have to be invertible to give i's. The i's and phi's both have to be analytic and so on. There's actually a natural way in which you can define Lie groups on differential manifolds, but this will automatically follow as a consequence. I'm just talking about the vectors and parallel to that. But just like vectors defined using components are very useful, this version is useful. So we are going to stick to that. Useful, and unless we want to take a huge detour into differential manifold theory, this is sort of the only thing that we can do at this stage. And I'm not going to really show you how this definition leads to the entire structure of Lie groups, because that's too long. And as I said, our main aim is to get into the algebras as soon as possible. So let's make the first attempt in that direction. Okay, one important tool in the theory of Lie groups is notion of one parameter subgroups. So what are they? Well, basically, first you'd start with the notion of a curve. Again, this is a differential geometric notion, but because we are talking in terms of components, we're essentially going to say something like this. Curve C is a map which is an interval on the real line. Okay. Well, once again, those of you who have done advanced maths would know that when you say continuous map, The curve really is a map, but we often confuse the map with the image of I under the map. So when we say curve, we really don't mean, say this is a manifold, we don't really mean the curve is this. We mean the curve is a map which takes I, say some curve C, okay, C, sorry, I should not really use this notation, that's reminiscent of the complex numbers. But you have a map which takes every point of this interval I somewhere in the manifold M. Okay? It's a map which is really called the curve. However, very often, and this is more consistent with the way we talk about curves in our daily world, the image of I, that is this bunch of points, is what we refer to as a curve. And sometimes we are going to confuse our language and talk of these points as a curve. Frankly, it's not going to lead to much of trouble unless you are being. Okay, sorry about that. I had a message from the other group. Wait a minute. Okay. So what does this curve do? It assigns to every point in the interval some element of the manifold that we're talking about. In this case, the manifold is the group. So some elements of the group. So G of, so what we have is we are going to have things like G of T. Okay. Now that's abuse of notation. What we really mean is, right? Because this G depends on R parameters x1, x2, xr. When we say we are on a curve, what we mean is I have a single parameter T as that changes x1, x2, xr changes, and hence the group element changes. So for all T on I, we have a situation like this. Okay. So that's a generic curve on your Lie group. The important thing is a one parameter subgroup, the thing which I'm talking about now, subgroup of G, is a curve and you can see the abuse of notation here. What we really mean is whose image is, right? Because when we say it's also a subgroup, what we are saying is take all the elements as you move along the interval I, you get a bunch of elements which are in the group, and if you collect them together, do you get a subgroup? If you do, then what you have is a one parameter subgroup. Of course, the parameter is the parameter T, which is running on the interval I. Okay? Clear about this? So what we have is something like this. We must have this thing. For all st belonging to I, g of s, g of t, there must exist a w in the interval. And sometimes because we want to avoid this problem of being of st being inside some finite interval, w being outside that, sometimes people just say let's take the entire real line and not bother about possibility of not the entire real line being used. But that's really mathematically incorrect. You have to ensure that if your S and T are taken from whatever interval defines your curve, GSGT is going to be parameterizable by some parameter W, some parameter value W inside your interval. And there must exist a parameter, let's call that S bar with a bar on top, such that GS bar GS equals E. And this W will of course be some function of S and T, and let's call that F for the time being. Okay. So is this idea clear? This seems like a trivial thing to say. You might say that okay, we had a group which had R parameters. We are now focusing on a group which has only one parameter. Of course, if we had focused on a group with only one parameter to begin with, then we wouldn't have a vector x. We would just one parameter. So whatever I'm saying here would be automatic for that. However, you have to realize that what we are really saying is something else. We are saying that okay, we have an R parameter group, but within that R parameter group, if there exists a one parameter subgroup, that means when I say g of s, I really mean g of x bar of s. Then I really mean g of x bar of t. Those functions. Okay. So put them together, what you will get is g of phi of x bar s, x bar t. And I'm demanding that these components somehow must be equal to x bar w. The bars are essential to remind you that these are R component objects. Whether these are this for example is the R function, R different functions. These are of course R different numbers, and all of them are controlled by single parameters in that R dimensional space. Okay. Now, the important thing is this T of course gives you a parameterization of the this T which runs over the interval I gives you a parameterization of the curve, but it should be easy to understand that you can choose to parameterize the curve in many different ways, right? You could say even go along the same interval I at a different rate. Instead of going around it fast, you may, or uniformly, you may want to go around it slowly to begin with. Slowly. Here, when I say slowly, I of course I'm implying that t sort of plays a role of time. But as you change t by the same amount to begin with, you move only a little, then you move a lot at the end, so that the entire interval is covered. All kinds of possibilities are there. Okay. The one important thing is we can always choose a parameterization. I always keep on getting confused about the spelling here. I hope this is right. So in other words, what we are doing is we are going to choose our parameters in such a way, the one parameter in such a way that when I assign it a value 0, I get the identity. Of course, I must get the identity for some value of the parameter, right? You are saying this is a one parameter subgroup. Being a subgroup, the identity has to be in there somewhere. So whichever point in I ends up giving you E, I assign that point in I the parameter value 0. This is just a choice. It makes life a bit easier later on. That's all there is to it. But once you do that, there's an immediate consequence for the function F. This is what you must have. Now, a single parameter function, which works only within the single parameter subgroup, of course, you must obey this simple property, which is very reminiscent of the property of the phi alphas that we talked about. But there we were talking of properties of R functions of two R variables. Here we are just talking of a function of two variables. If the first argument is 0 or the second argument is 0, you are going to end up with the other argument. Okay. The all important result which you need here, and that's the critical result for us, is can always choose a parameterization so that, and this is so important that I'm going to write it in a different color, f of s comma t, that is how the parameters combine, is given by S plus T. That is, you can always find a one parameter additive subgroup. Are there any questions about this so far?
How are we sure that such a parameterization exists?
Yeah, so that's an important question, of course. Uh, and that is the one important result from group theory which I really should prove for you. Okay? That a one parameter one parameter or a parameterization for the one parameter subgroup always exists such that the parameters add when you compose group elements. And that's critical in defining all the properties about Lie algebra and exponentiation and all that. But before I go into the proof of this, can can you give an example of, say, a one parameter subgroup from a familiar group? Let's say the rotation group.
Rotations about the same axis.
Yeah, if you rotate about a given axis, say any fixed axis whatsoever, the infinitely many one parameter subgroups, of course, rotate about any fixed axis. And what is the parameter? The parameter here has an obvious choice. Take the angle theta, right? Okay. And if you do that, the composition rule becomes simple, right? If you rotate about, so when you say RZ theta and RZ theta 1, RZ theta 2, you really are talking about a parameterization of the full rotation group where the axis is already labeled and you are just varying theta 1 and theta 2. But when you do that, you end up with RZ theta 1 plus theta 2, right? That is additive. Is that okay? So at least for the rotation
Sure.
group, yeah.
Sir, but RZ theta 1, these are uh, continuous because it's a matrix representation,
Yeah.
right? And over here we're talking about groups which are continuous,
No, that's
and
what
they
I
are
said.
not
I will not
represented.
worry about what it means. That's where the differential manifold structure of the Lie group comes in. Okay. That's a different question altogether, by the way. Conti- can we talk about continuity? The answer is the continuity has to be, when you want to talk about continuity, you must always have a topology on both spaces. On the original space, which is the R dimensional space of real numbers, which already has a topology, standard topology, and the topology on the Lie group, which is on the manifold. Now, the differential manifold structure already imposes a topology, and you can use the topology to prove these continuity and all other statements. But we are not going to do this in the abstract simply because it's going to take way too long to get there. Okay? But that has nothing to do with this particular point I'm trying to talk about. All I'm saying is here you have rotations about a single axis, whatever that axis is, you end up with this. So the compose, so theta 1, theta 2 are the two parameters, and they compose to give you this parameter, which is theta 1 plus theta 2. This and the question of continuity are two entirely different things altogether. And as I said, I'm going to avoid the question of continuity on general groups anyway. Why? Because most of the groups we are going to deal with are matrix groups and their continuity is sort of obvious. So even if we wanted to be rigorous, at least for those groups, we can easily be rigorous. For a abstract Lie group, it's not so easy to be rigorous. It's going to take a huge amount of time just worrying about those questions. We simply can't afford that amount of time. But this is a different point altogether from this, the fact that you have this additive property. But can I just ask you one thing? Um, First of all, is theta the only possible parameter that I could use?
Any
Any monotonic
scalar
function of theta would do, right?
yeah.
In fact, if theta is confined to within 0 to pi, which by the way, this is not. This is, in fact, this is not really additive over the entire interval. This is theta 1 plus theta 2 mod 2 pi, right? But at least locally it is. And locally is all you need. Uh, if instead of theta, say theta were confined to from 0 to pi, which is what we talked about in our parameterization, then cos theta is a perfectly good parameterization because cos theta is monotonic between 0 to pi, right? You know that, right? You all know that. That's between from 0 to pi, cos theta is monotonically decreasing, right? And you do realize that is why cos theta plays a huge role in all kinds of calculations we do with spherical polar coordinates. Not sine theta, it's cos theta which is important. That when we do a variable substitution, right, for say when we go to the Laplace equation, we do a substitution of variables. Instead of theta, we choose a new variable. The variable we choose is cos theta. That's not arbitrary. Cos theta is a one-to-one correspondence in that interval. Sin theta wouldn't have been, right? So it's not completely arbitrary, those steps that we did, that we replaced theta by cos theta and wrote a new differential equation, which ultimately gave us the legendary differential equation. Those were not arbitrary steps. They were forced upon us in a way. But here, if instead of using theta, you use cos theta as your parameter, of course you would not get additivity, right? But still have a single one parameter subgroup, which is a subgroup which is
Sir,
parameterized by a number.
sir, would you please repeat why not sine theta? And I mean
Because
that
because
argument.
theta to sine theta is not a one-to-one correspondence on 0 to pi. Between 0 to pi, this is what cos theta looks like, right? What sine theta looks like is this from 0 to pi. Why 0 to pi? 0 to pi is a range of values for the angle theta in spherical polar coordinates. This is
So
what
the
sine theta
function
looks like,
is
right?
not one to one.
It's not one to one. And that's why you don't use it. You use cos theta, which might come as a surprise if you're doing it for the first time because cos seems to be something which we think about only after we have exhausted things about sine. Sine is the first thing we learn about, right? First of these trigonometric functions which we keep on using everywhere. But sine would simply be a bad choice. There are many things that are those steps that we do. They have some tiny mathematical implications which are built in, which are often taken to be obvious. But I'm not sure whether that's obvious to everybody that you can do this thing that's z equal to cos theta that you do all the time. That is something you can do because theta and z are in one-to-one correspondence over the interval 0 to pi. That's not true for sine theta. That's why you don't use sine theta. If you substitute a sine theta, you will land up run into all kinds of trouble with singularities and all that. But that will essentially happens because of this bad choice of the transformation. Okay, that's taking us too far afield. Let's get back to this. Uh, what I was trying to emphasize is that the one parameter subgroup is additive seems to be sort of obvious for rotations, but that's because for rotations, the parameter that we usually think about, the angle, is a natural one for this additive business. But if we're using theta, we had used cos theta. Okay, then what would have happened if I had used z here? I would have ended up with Rn z1, Rn z2 would have been Rn of, well, cos of cos inverse z1 plus cos inverse z2, which you can of course figure out how what that is. That's z1 into square root of 1 minus z2 square plus z2 into square root of 1 minus z1 square. It would end up looking like a horribly complicated function, right? So f of z1 z2 will be something which looks like this. It just is lucky for us that this is not the parameterization we see naturally. But if we had started looking at this parameterization of the group, or this one parameter subgroup, from this realizing that there is a change of parameterization you could do so that you will end up with a additive parameterization, that's not so obvious, right? Is that okay? Of course, here you know that if you land up with this, instead of using z, just use cos theta. That is, take z to be cos theta. Then immediately this will give you theta 1 plus theta 1 theta 2 will give you theta 1 plus theta 2 for this new change variable. But that's because here we know that because we cheated. We already had this additive behavior. We deliberately broke this by doing this change, so we know how to undo this. But the question that was asked quite rightly is how do we know that we can do this for a general group? Before answering this, I would once again like to draw attention to another group for which one parameter subgroups are things you already know about, but where things are not so obvious immediately. Okay, the Lorentz group. Can anybody give me examples of one parameter subgroups of that? Of course, there are rotations about an axis. So those we have already seen. Any other one parameter subgroup of a Lorentz group? Yes. Even if you don't know the details of the Lorentz group, this should be sort of obvious.
Translations in one direction.
Translation is not a Lorentz group element. That's a Poincare group element. Translations in one dimension is a one parameter subgroup of the Poincare group, and there, of course, again you have additivity of the parameters, rather trivially. But yeah, any other choice? Lorentz group, focus on the Lorentz part of the name.
Boost in one
Yeah,
direction.
boosts in one direction, right? Translations are not Lorentz group elements anyway. And when we say Lorentz group, of course, only later on we learn enough to understand that rotations are also Lorentz transformations. But the first thing that we talk about are boosts, right? Boosts, and if you boost along any one axis, two successive boosts along one axis is a boost along that axis, and that's a closed set. That actually is a subgroup. Okay, boosts along any one axis. What would be the parameter used for this? How will you parameterize this?
Velocity.
Velocity. Or usually we don't use velocity, we use beta, which is velocity by speed of light, right? But if you're boosting in the z direction, in say the x direction, you do get a boost in the x direction, but the parameter for that is not beta 1 plus beta 2, as you all know. That's this famous velocity addition rule. This is what you get, right? So at least in one common example, we had an additive parameterization. That's what rotations. Here, for boosts, we don't have an additive parameterization, at least not immediately. But I hope all of you know that you can find an additive parameterization. Do you know that?
Hyperbolic function.
Close, yeah, but which hyperbolic function? And there's a name for that.
We can express the beta by hyperbolic tangent of the rapidity.
Right. And why do we do that? Because if you do that, the rapidity essentially adds. So that's simply a parameter change, right? You're changing from the parameter velocity to a new parameter rapidity. And the reason why you do that is that rapidity adds under Lorentz transformation. Okay, so if you define beta as tan hyperbolic phi, then you end up with LZ phi. That's an abuse of notation. Of course, you should really change the letter LZ for something else, but doesn't matter. Or LZ LX, whatever, doesn't matter. Phi 2 is LZ phi 1 plus phi 2. This is the rapidity, a new parameter which is often used instead of beta, especially in more advanced calculations, simply because the maths becomes a lot simpler. You can add up. Okay? And this ability of adding up is actually critically important for this D group Lie algebra connection, as you will soon see. Okay? Um, by the way, my favorite parameterization for at least one dimensional Lorentz group is actually not the rapidity is that's an aside, but it's really the exponential of the rapidity, which is called the Doppler factor, because that becomes multiplicative and lots of nice calculations can be done with that. Okay. However, rapidity also is quite nice basically because it just adds, and for Lie group structure that's important. So of course, two examples does not make a proof, but what we have done is we have shown that at least for two of our favorite Lie groups, we do have one parameter subgroups, where in one case the additive nature of the parameterization was obvious to begin with, unless we rather, well, rather nastily decided to use a different parameterization. And for the Lorentz group, we had this one parameter subgroup of boosts along any particular direction, where we did not have a natural choice to begin with, which gave us additivity, but we could easily change over to a choice which did give us additivity. The question that was raised, of course, is can we always do that? And the answer is yes. Okay, and let me quickly indicate how that proof goes. Basically, what you do to prove this is start with a parameterization where this additivity is perhaps not there. Let's just say we start with an arbitrary parameterization, and just because we are going to go on to a better choice later, let's indicate this parameterization with primes. So if you have a parameter S prime, that gives me a group element GS prime somewhere in the manifold. So this point denotes the group element for us. And then GT prime and so on. Okay, let's start with GT prime. And so let's take a fixed T prime in my interval, whatever interval I'm using. Then multiply this by, okay, not multiply the T prime, but multiply the group element by GS prime. So this gives me some group element G of W prime. So GW prime is simply G of S prime, G of T prime. I'm saying that GS, this means multiply by GS prime from the left. Okay. And this W prime is some function, some complicated function, let's call it F prime of S prime T prime, not necessarily an additive function. The claim is that because of the basic properties of the Lie group, or the basic group properties, really, we should be able to find new parameterization which is additive. And how do we go about proving that? The answer essentially lies here. Just look at change S prime slightly. So you get GS prime plus DS prime. Of course, this is infinitesimally close. I'm just drawing the points separate just to sort of show you what's happening. Maybe I've started too close to the top of the page. Let me just try to pull it down a bit. Yeah. Okay, so this is point is G of W prime plus DW prime. Of course, what we are going to claim is because our parameterization is smooth and continuous, if you change your S prime slightly, the parameters W prime is going to change slightly to W prime plus UW prime. Okay. So this, of course, tells us that W prime plus DW prime, the parameter, is nothing but the function F prime, this function, where you get the arguments S prime plus DS prime and T prime, right? And this immediately tells us, assuming that all these functions are smooth and analytic, which is, by the way, the critical part in the definition of a Lie group. What would you do if you ever saw an argument like a situation like this? What would you use?
Taylor expansion.
Yeah, right. So you would do something like this. In fact, you don't even look at the higher order terms because this immediately tells you that dw prime is this term. Actually, While this is correct, we will not really look at this directly. What we will look at is look at this in a slightly different way, which exploits the group structure even better. Note that since GW prime plus this point is close to W prime, you should be able to get from here to here. That is, instead of going GS prime takes the GT prime to this. As GS prime plus GS prime takes GT prime to this point. But instead of going this way, you could start at GW prime and hit this by a small or an element which is close to the identity, right? That's what small means here. Some delta S prime, but delta S prime, of course, should depend on what ds prime is. So what you are saying here is should also be equal to g of delta S prime, g of W prime. The reason why I'm doing this should be clear very soon, but this tells you that in this way of looking at things, W prime plus dW prime is what? It's actually sorry. How much is this? This is going to be f of delta S prime W prime. So that is fine, but this actually makes life a bit easier for us because this is again a Taylor expansion, but this is a Taylor expansion where one argument is 0, right? Delta S prime is infinitesimally close to 0. So if you use that, the first step will be f, okay, f prime, let's call this f prime as I've been calling it. So f prime of 0 comma W prime, that's of course W prime, plus it's 0 comma W prime. Sorry. So this is what dW prime is. Okay. You just expand Taylor series to first order and match the differentials. This is what you're going to get. So this is basically lambda S prime is simply a definition of this. That is, you differentiate your function f prime with respect to the first argument and put 0 in the first argument. So this of course becomes a function only of the second argument. Wait a minute. I messed up. This is wrong, of course. Can you see why this is wrong? What will this quantity depend upon?
W prime.
Right. This will not depend. It's a function of W prime. So is lambda the function, some function, which is just this first derivative, evaluated at W prime. Okay. So this is what you get for dW prime. Well, lambda by definition is simply lambda at some argument. Let's not use stw, let's use some other variable name. Lambda of u prime is by definition, take the function f prime, differentiate with the first argument, then put in 0 comma u prime. The first argument s prime is put to 0. Whatever the second argument is, of course, lambda will depend on that. So that's our definition for lambda. Here you get dW prime is lambda W prime delta S prime. Now, if you look at our original premise, this is what you had. It was g of delta S prime GW prime, that is g of S prime GT prime, right? That's what GW prime is. It's also g S prime plus ds prime GT prime, right? So this immediately tells us that g of, this is where the group structure becomes very important. Because it's a group, you can cancel out the GT prime and you get GS prime plus ds prime is g of delta S prime ds prime. Okay, so all we have done, sorry, could I just put you on hold a bit? Sorry about that. Another urgent call came in. But anyway, uh, I hope nobody has lost track of the argument. I surely have. Anyway, let me just quickly tell you, we had GT prime. Everybody is still here, right? More importantly, I'm still here.
Yes.
Okay. So we essentially looked at two different ways of getting to a point G of W prime plus W prime. One is by hitting GT prime on the left by GS prime plus GS prime. The other is by hitting with GS prime first, then hitting with G delta S prime. Okay, so a two-step process. But that because of the group structure, this is what immediately came about, and therefore S prime plus ds prime must be f of delta S prime comma S prime, and this gives us, with a very simple Taylor expansion once again, so ds prime is lambda S prime ds prime. So notice that, yeah,
Lambda S prime, delta S prime, sir.
yeah, this is delta. Sorry, yeah, of course, of course. The last line. This is an absurdity, whatever I wrote. So yeah, delta S prime. But now focus on these two equations. You have how much the parameter W changes, you have how much the parameter S changes. Okay, and there's this common delta S prime sitting in both of them. So the immediate thing that anybody would do is realize that this tells us that dW prime by lambda W prime is ds prime by lambda S prime. Okay, right? The delta S prime, whatever that was, that has sort of vanished from this scenario. That is cancelled out. Okay, and now if I integrate this equation, both sides of this equation, starting from, okay, I should really call this S double prime because I'm allowing S prime to change from 0 to S prime here. Okay, and that's the same as, okay, let's call this W double prime even. Just as a dummy variable of integration. But when S is 0, S prime was 0, what was W prime? Remember, this is the scenario. GT prime, heading with S prime, you are going to W prime. So when S prime was 0, here what we are doing is we are allowing S prime to vary, keeping T prime fixed. When S prime was 0, how much was W prime?
T
When S
prime.
prime is T prime, right? Because when S prime is 0, GS prime is identity. So you're not moving at all. So this is the initial value of W prime as S prime ranges, or S double prime, which is the dummy variable of integration here, ranges from 0 to its final value of S prime. This goes from T prime to W prime. Right? Is that okay? This is just definite integrals. They're just putting the appropriate limits. Okay. Now we are done actually. How are we done? All we do is we define this new set of parameters. You say, okay, let's take dx by lambda x. Let's integrate from 0 to s prime and call that s. Okay. You can easily show that this is a perfectly valid reparameterization. I will leave you to worry about the issues about one-to-oneness and so on, but you should be able to do that. And you do something very similar, not only for S, you do it for S, T, and W. That is, basically you say, take your old parameterization, whatever that was, and integrate dx by lambda x from 0 to the new parameter, old parameter value. You get a new parameter value. In other words, you define dx by lambda x integral from 0 to W prime as your W, and do the same thing for T. But if you do that, then it's obvious that W will be S plus or W minus T, which is the integral of dx by lambda x from 0 to W prime minus that same integral from 0 to T prime must be this integral. Simple property of integral calculus. And this must follow. Is that clear to everybody? All we are saying is group theory imposes this restriction on how much the parameters will change. Okay? This lambda is some function which comes from this derivative. But the same function on both sides. Whatever lambda is at w prime, you divide dw prime by that, you get the same as ds prime by lambda s prime. Once this is true for all values, this integral immediately follows. And then just as a simple reparameterization, w minus t equals s works out. Okay, I will leave you to think about this a bit. All I'm saying is, given some parameterization which was not necessarily additive, by carrying out this this transformation of variables, you can go to a new parameterization which is additive, and that additivity is guaranteed by a basic property of integral calculus. But the important thing here is this result, which follows from the fact that we have a group. If we did not have a group, we would not be able to cancel out gt prime, we would not have had this result, and we would not have ended up with this simple thing. Of course, not only group, you have a group where you can tailor expand the parameters. That's the analyticity at work. So the entire structure of Lie groups, that is, you have a group structure, you also have the ability to do calculus, all of this put together goes into this proof. Is this okay with everybody? Even if it's not, I will let you think about it. It's something which is, this is the only non-trivial result from Lie group that we are going to need. Okay. And the result is simple. Result is every one parameter subgroup can be parameterized in such a way that composition rule becomes addition. So you often call this a one parameter additive subgroup, but you should realize that the additive name is adjective. It's something which you don't really need. It's not a additional classification because every one parameter subgroup can be made into an additive subgroup. Okay. So the deathly silence is telling me that this is not really getting through. Maybe the intermission was not very helpful. Okay. Can I move on to the next topic? Or do I need to explain this again? Okay, a silence on a yes or no question seems to make me think that you are all cut off.
No, no, so you can move on to the next topic.
Okay, I will move on to the next topic because basically because I think people have given up on this. Anyway, this is the important thing. Okay, everything. Because why is this important? Simply because the critical thing that we do, which is treat the Lie group in some way as an exponentiation of the Lie algebra, that's critically dependent on this. So what is the basic idea there? The basic idea is if you start with sorry. Suppose you start very close to the identity and ask questions like this. Remember we had this demand of our parameterization. This is, we are back to the full group, but so this alpha is the vector alpha. And when you put it equal to 0, you get E. Okay. So it's easier to talk of this in the concrete rather than in the abstract. So we'll talk about some matrix representation the group will have. Ultimately, we are going to use the matrix representation all the time because that's the one we are going to use. So this is what you're going to get. The corresponding matrix will be the identity. So for every bunch of parameters, R parameters, you will get a matrix, and if you replace the R parameters by 0, all of them, you're going to get the identity. So what happens if you make the R parameters tiny, not zero, but some tiny value? By now you should all be familiar with this. What happens is you get the identity plus, right? Now, this is why I'm going into the representation. I'm actually, okay, I'm cheating. I'm making exposition easier for myself without talking about the abstract group, simply because we are going to two things. We are going to use the matrices anyway. And more importantly, for us right now, matrices are quick way of talking about these things, because matrices, of course, there you have an algebra. You can add and subtract and so on. When you say G alpha is identity when alpha is zero, and is going to be close to the identity when alpha is infinitesimal. The problem is, what do you mean by close to the identity? It's not identity plus something, right? Because on a group, plus is not defined in general. So what we are doing is, we are, instead of looking at the group, we are looking at a particular representation of the group, which happens over a vector space, and these you could also either say these are operators which act on the vector space, or be more pedantic and say these are matrices which describe those operators. In either case, addition is easy. So we can easily see that when alpha equal to 0 gave me the identity, and very tiny alpha will give you something very close to the identity. This, of course, is what we do naturally in the theory of rotations, and we get angular momentum as generators and so on. So these A's are called the generators. These are matrices if you're using matrix version, or operators if you're on whatever vector space your representation is in. So the same Lie group, of course, will have different generators depending on which vector space the group is acting upon. Okay, so different vector spaces give rise to different representations, different sets of generators. So the generator of a particular group, that doesn't really make sense. Generators depend on which vector space you're using. And from the theory of angular momentum, it should all be clear to you, that this should be very familiar to you at least. Now, what physicists always do, and many mathematicians hate us for doing that, is that we throw in an I. Most mathematicians don't. And as I explained in the last class, the reason why we throw in an I is that we want, uh, especially when we are dealing with unitary representations, which is what we do all the time, okay, we want this X's, these generators, to be Hermitian. Of course, we even mathematicians love unitary transformation, unitary representations. The obsession with unitary representation is not a physics thing. What is important is, physicists love the Hermitian operators a lot, basically because Hermitian operators are observable quantities and so on. A mathematician usually is under no such obligation, so mathematicians often just drop the I, live perfectly happily without it, and in fact live more happily without it, because they have a more consistent theory as a result. But as I was saying, let's. So I hope that point was clear. That's something we talked about the other day, right? If my memory serves me right.
Yes,
And
sir.
okay, so this I is sort of physics thing. Some mathematicians also use it simply because they have been influenced too much by physics. But most mathematicians don't have an I, and that's why mathematics books and physics books differ. Anyway, this XR, of course, nothing but the derivatives of the D with respect to the alphith component at the origin. So, in a sense, the information that XA has basically is information about what's happening near the origin. Now, if this were general function theory, then if you know what a function is near the origin, that gives you no clue whatsoever what it's going to do far away, right? Because this definitely will, for example, if I just told you that, okay, this function, I have a function y which starts off at y plus dy is, say, some y0 plus 3 dx. plus higher order terms. Would you ever even try to tell me what the higher order terms are going to be? Yes or no? In other words, you know the first derivative. Will that knowledge, first derivative at a point, remember, not first derivative everywhere. If you know the first derivative everywhere, that's a different question. We keep usually get confused by this, but the important point is this 3 is the first derivative, not the first derivative function. It's not the first derivative everywhere, it's the first derivative at x0. If you know that, does that tell you anything whatsoever about the second derivative even at x0? The answer is no. Or the third derivative or the fourth derivative. All these higher order terms you simply can't figure out by the knowledge of the first derivative at x0. That's a general scenario. But this one parameter subgroup business gives us a clue as to how we could overcome that for the Lie group case. So this is specific to the Lie group structure that you have. And there, what you would say is, okay, I can always find one parameter subgroups. Remember, we are not saying that all elements would fit into that, but I can find one parameter subgroups such that if you have a big parameter alpha, that big parameter alpha can be found out by adding alpha by n times. But that of course means because uh, adding parameters in for our one parameter subgroup basically is akin to multiplying group elements, and of course multiplying group elements means multiplying representations. This must be d alpha for but this is the critical part in our argument, that you can always find one parameter subgroups. Number one, in fact, you can always find one parameter subgroups going through every group element. That's sort of easy to figure out, not a difficult thing at all. Okay, and every one of these one parameter subgroups can be individually parameterized additively. Is this clear? So I'm making two statements here. Are both of them clear? The second one we have just proven a while ago. Even if the proof is not very clear, at least that's the proof. But the first statement I did not really state before. So it's a new statement. I'm saying give me any group element, there will be a one parameter subgroup which contains that group element. Can you prove that? It's very easy. So if I have a group element, say g of some alpha vector, where alpha is some bunch of parameters.
Are the parameters additive here?
Not necessarily. Okay. Once you find a one parameter subgroup, then what you would do is once the one parameter subgroup is available, all you have to do is then carry out the process that we talked about and make it additive, even if it's not additive to begin with. Here, in general, in the group, in a general group, the parameters are not additive anyway. The function phi alpha may be very complicated. That is what the whole point is. The point is, no matter how complicated your original composition rules are, you can always find one parameter subgroups and you can always reparameterize them so that they are the parameters additive within the one parameter subgroup. Just to uh, sort of stress what I'm talking about here, go back to the rotation group. You have one parameter subgroup which are pretty familiar, right? Rotations about a given axis. But the parameters for the overall group is not definitely not additive. It's pretty complicated, right? A rotation about the x-axis through angle theta, rotation about y-axis through angle theta 2. That gives rise to some rather complicated combination, some complicated rotation, right? Not a simple parameterization at all. So the original group may have a very complicated composition too. All I'm saying is, no matter how complicated the rule is, one parameter subgroups can always be reparameterized to be additive. And this is the statement which I missed out then. Every group element belongs to a one parameter subgroup.
We can generate a subgroup by acting g of alpha bar on itself, like the subgroup generated by g of alpha bar. Will it be one parameter subgroup?
No, not really. but you're close. What you can do is just take any one parameter subgroup you have. Okay, I will leave you to worry about how to show that there is one to begin with, but that's sort of implicit in what we have done so far. Take any one parameter subgroup. So I should really perhaps change the notation a bit. Okay, if I don't use a bar, it's a member of the one parameter subgroup. And multiply G alpha bar either on the left or the right. I don't really care too much. Okay, let's, for the sake of definiteness, let's say on the left by GS. And let S vary. S is a single parameter that varies over U interval. Okay. So this of course will give you a curve on the manifold. You will be able to show that you get a group this way. And you should also be able to show that that G alpha bar definitely is inside that group.
Showing G alpha is in the group is easy, but how can we show that it's a close, like GS
It's
G
not.
alpha bar, GT G alpha bar?
Hmm? So let's say this is additive. Let's say this one parameter subgroup. This one parameter subgroup I have, I could make it additive. Okay. Now this will not work, by the way. This, and you're right. This is wrong. Okay, you are right. This is wrong because if you take this and take this, you cannot show that this is G of some W, G alpha bar. Correct. But what can you do to change the prescription I gave you right now to show that it can be done? Just think about it a bit. This can be done rather easily. All I'm saying is this prescription I gave you is wrong, but there is a very simple prescription which will do the job, which is very closely related to this one. So this is a puzzle for you. How would you go and find a one parameter subgroup going through G alpha bar, given that you have some one parameter subgroup which goes to the identity? That should be a sort of big hint. You've done enough group theory over the last 2 days. This is a very standard thing that you do in group theory. One very standard thing you try to do. So I will leave you to worry about whether that can be, whether you can solve this problem. What I've said right here is wrong, as you have rightly pointed out. But there's a very easy way to correct this. And that's something which
G
I'm going to
alpha
ask
bar
you.
inverse.
Hmm?
G alpha bar inverse on the left. Then if I multiply, uh,
Then how do you ensure that it goes to G alpha bar?
no, since G alpha bar is not additive, so I cannot cancel out
And
G
even
alpha.
even if it were, then the alpha bar would cancel, and you will not be left with G alpha bar at all.
No, so he meant G alpha bar
No,
inverse GS G alpha.
Yeah.
yes. Then if I'm multiplying it, then G alpha bar and G alpha bar
Then you can,
inverse will cancel out.
first of all, think about it. You're close, but
If you multiply those two terms, then you get G of S plus T on G alpha inverse and G alpha on either side.
yeah,
So it does satisfy the composition rule.
true. But does it really help? Because in the sense that does this go through G alpha bar?
It doesn't. It doesn't.
By the way, it would if you could show that your one parameter subgroup GS for some parameter value GS, for some
G
parameter value
alpha.
S, GS is G alpha bar.
Yes, that would have
Then of
worked.
course
But
these two
yeah,
will cancel and it will go to G alpha bar. But then you are assuming that your original one parameter group actually goes to G alpha bar. What you have managed to show actually is an interesting result, by the way. You have essentially managed to show that if you take a one parameter subgroup going through one point, you can actually generate infinitely many through that point by using this conjugation argument. However, that doesn't fit what we wanted to do. Think about it a bit more. But why you need that is simply okay. Let me just move on to why we need that for. So that's a puzzle, not a very difficult one, and you are very close to answering that. But Well, the rest is straightforward. If you know that you can always choose a one parameter subgroup which goes through that point, so whatever point you are landing up with has some parameter value, but that's a large parameter value. But because you have a one parameter subgroup going through the point, that large parameter value is a single parameter, large value. But because it's additive, you can break it up into pieces like this, and then you can immediately say that this will give me same as, because this is true for all n, so it's true for even for the limit n goes to infinity, I alpha by n xa, sorry, alpha a, alpha. So when I say alpha, so there's a bunch of parameters, and these bunch of parameters will go like this. Remember, these are okay. When I say one bunch of parameters, I mean all of them are controlled by a single parameter. All of them are essentially proportional to one given parameter, which goes all the way from 0 to 1, and these parameters all go from 0 to alpha a, alpha 1, 0 to alpha 2, 0 to alpha 3, and so on. And okay, so this is usually taken to be the starting point for most Lie algebra things, that you can actually write down group elements or representations of group elements at least in this form. The reason why you can always do that, okay, the reason why you can always do that is because of this one parameter subgroup which exists, and because of the fact that you can always reparameterize that. Okay, so I will just quickly um, recount for you the reason why. Of course, from here, the next step that you do is you will say that these are the generators, and the commutators between generators are all important. And you say the commutators has to be another generator or linear combination of generators. So you write things like FABC with an I thrown in. Okay. Uh, that's what we are going to prove on Thursday. That is why this has to be the case. And what properties does this? So after we come here, basically what we end up with is these generators, which are Hermitian operators, at least in our physics based applications, but not necessarily always. And these Hermitian operators have commutators which in a sense is closed, but as has been pointed out last year also, Hermitian operators can't really be closed under commutation. You have, you have to throw in an I to ensure that. Anti-Hermitian operators, on the other hand, are closed under commutation. So the mathematician's choice of dropping the I actually leads to a cleaner mathematical structure. So next year what we are going to do is we are going to take a look at why the commutator is sufficient. That is, you don't really need to know anything more about the generators, just the commutator will tell you all that you want to know. The full proof is rather complicated. We'll give a sort of mangled faces proof of that. Okay. And then we will try to see what we can deduce from these constants, which as you all know are called structure constants, and what kind of basic properties you can impose on the Lie algebra. And we will try to quickly see what kind of structures Lie algebras can have. So maybe all that can't be done on Thursday, but some of it can be. So all of you know that. Do you all know this? That why is the XAXB sufficient and so on? Then I can move on to other things.
Because of the Baker-Campbell-Hausdorff formula, we can get any element of the group element from this thing.
Yeah, the basic idea is simply is that although these are nice exponentials, so as long as alpha a is proportional to each other. So if I took exponential I alpha a x a and tried multiplying this by exponential I beta b x b, if we had this result that beta a by alpha a is the same number, let's call it mu, for all a. then it's easy to see that what you are going to get is e to the power I alpha A plus beta A xa. So that is the parameters really add. But that's basically, we are saying that this proportionality is basically what we mean when we say that we are within the one parameter subgroup. But in general, when this doesn't work, then this is not true. But as you have rightly pointed out, the point really is we are going to claim that despite that being not true, I'm going to get some elements. And to find out gamma C, all you really need to know are these commutators and nothing else is going to be needed. First of all, the very fact that this has to be of this form, that is, has to be a group element, all group elements are of this form. So that this has to be of this form immediately tells you that this has to be closed. That's one part of the answer. That is, why does a commutator have to close? After all, that's not so obvious, right? The fact that the commutators have to close essentially deals with this. Because every group element can be expressed this way. So if you compose two group elements, you will get a group element, and that demand tells you that the commutators will have to close. That's the part I'm going to really show. The other part is, as you said rightly, that it to show that the commutator is enough, you have to actually prove the Becker-Campbell-Hausdorff formula. If you don't know what the Becker-Campbell-Hausdorff formula is, that's too much hard work, so we are not going to go into the full proof of that. But such a formula does exist, which tells you that if you know the commutator, you can find out gamma C to all orders. But what we are going to address is perhaps the more important question, which is why do the commutators have to close in the first place at all? Okay, so we will see that in the next step, and then we'll see what properties are imposed on these constants FABC, and what conclusions can you draw from them. So let's meet on Thursday and try to get most of the Lie algebra theory out of the way. Then we'll talk about specific examples. I'm hurrying a bit, I know, but getting too close to the end of the session for the luxury of time to be used. Okay, but all of you make a list, send me a list of your proposed presentations, and then we can schedule this. Okay? Take care. So bye for today. Huh? Let me stop the recording.